Okay, so stoichiometry is what we're starting today. And stoichiometry is where we're going to put all the pieces of the puzzle that we've been learning so far, and we're going to put them all together, okay? So we've learned how to convert from grams to moles and moles to grams. How did we do that? Do not say Avogadro's number. No. Molar mass, thank you. Molar mass. We learned how to balance equations. And we learned dimensional analysis. So we're going to put all that together now and learn how to do stoichiometry. Okay? So it's not that hard. For most of you, you're going to get it pretty easily. And so let's just do some housekeeping here. Okay, so first of all, stoichiometry is a proportional relationship. So proportional relationship between two or more substances in a chemical reaction. This stoichiometric relationship sounds like a very fancy word, but this can exist between moles, grams, atoms, or liters, volumes, milliliters, whatever, okay, or volumes. So you can have a volumetric stoichiometry relationship. Stoichiometry itself is the study of the amount of substance consumed or produced in chemical reactions. You must write it big and bold, always start with a balanced chemical equation, because the balanced chemical equation is going to give you that mole relationship between anything in the balanced equation, okay? And that's going to be involved in every step of a stoichiometry problem. It's going to have a mole ratio. So what is the mole ratio? It is based on the balanced equation, so always comes from the balanced equation. Whoops, forgot to tell I was writing. So always comes from the balanced equation. And the balanced equation will give you the mole relationship. Okay? So the coefficients, I'm going to abbreviate that. Are you okay with that? Because I write too big for that. Is equal to the number of moles. Okay? So this is the equation for the production of ammonia. So if I were to read that equation, the way I would read it is I would say 1 mole of nitrogen reacts with 3 moles of hydrogen, which yields 2 moles of ammonia. Yes?
Is that subscript a B?
A B?
Coefficient, is that subscript?
It's a period. I was abbreviating.
Wow.
Just I moved my hand too fast.
That looks like a nice period.
Or a 6. A little small. How's that? Now can you tell it's a dot?
Yeah.
There we go. So the coefficient, I just abbreviated because I write too big to fit that word in there. The coefficient, which is the big numbers that we balance with, is equal to the number of moles. So again, I would say 1 mole of nitrogen reacts with 3 moles of hydrogen, which yields 2 moles of ammonia. So how many moles of ammonia would be produced from 3 moles of hydrogen? 2 moles of ammonia. Okay, so you could look at it that way. How many moles of hydrogen would react with 1 mole of nitrogen? 3. Okay, which is all great and good if we're dealing with the same amount of moles that we're dealing with in the problem. Okay, and so you can have this mole relationship with anything in the problem. It can be reactant to reactant, reactant to product, product to reactant. Okay, and you'll see all of those come up. Okay, so we're going to work a couple of problems with just the mole ratio, because that's the easy part, so that I make sure you understand how to use the mole ratio. Your mole ratio is going to be how you get from what is known or what is given to what they're asking for. Every problem will require the mole ratio. Okay? So here we have this problem if I want to know how many moles of ammonia are produced from 2.5 moles. So I'm going to go ahead and rewrite the equation up here since it's on the other page. And we said it made 2 moles of ammonia. Okay? I know you could do this in your head, but these are longer steps when we get past the mole ratio, so please set it up like I ask. Okay? So if I'm going to start with 2.5 moles of nitrogen, anytime I'm doing dimensional analysis, I always start with what's given to me. So I'm going to say 2.5 moles of N2. I want to get rid of moles of N2, so where do I put it? On the bottom. and I'm trying to get to moles of ammonia. So I'm going to put moles of ammonia on the top. Now I'm going to go look at my balanced equation and see what numbers are in front of it. What number's in front of nitrogen? 1. So it's 1 mole of nitrogen will produce 2 moles of NH3. So I cross out moles of nitrogen, and now I've got stuff on the top. I multiply the top, divide by the bottom. So I should get how many moles of ammonia produced from 2.5? 5. And how do I report that? Not 5 moles. The sig fig thing, yeah. So it should be 5.0 moles of NH3. The sig fig thing. That's another piece of the puzzle we have to put back in there. Okay? So in the next one I have 6.00 moles of hydrogen, and I want to know how much ammonia I can make. So I need to get rid of moles of hydrogen, so I put it on the bottom, and moles of ammonia on the top. And that relationship is for every 3 moles of hydrogen, I can produce 2 moles of ammonia. So now I do the math. 6 times 2 is 12, divided by 3 is 4. So how would I report that? 4.00, because I have the 3 sig figs there. Okay? Remember, you must always start with a balanced equation. If you do not balance the equation, you're going to have your mole ratio off, and then you will not get the right answer. Okay? So on this next one, I want y'all, we're not going to do example 1 because we've done ammonia 3 times now. So I want you guys to try to work example 2 and see if you get the correct answer. So I'm going to pause this. Okay. Did everybody get 4.6? 4.60? 4.60 with the correct number of sig figs. Okay. So make sure you're showing that these canceled out. Okay. Did you balance the equation first? Then that's good. You did the first step. Okay. So who did not get 4.6? Everybody did? Or you, oh, you forgot to balance the equation. So see, that's kind of showing you if you don't balance it, you're not going to get the correct relationship between the aluminum oxide and the aluminum. Okay? So that's just mole ratio. Most of our problems are beyond the mole ratio. So let's go to do beyond the mole ratio. This is something called the Stoichiometry Roadmap. There's a copy of it on Canvas if you want to use it. Most kids do not need it because it's pretty intuitive once we show you the steps and you're following your units. The secret, I told you this in the beginning of the year when we're doing dimensional analysis, the secret to this is always just let your units be your guide. Get your units, line them up to cancel out, and you can get to the correct answer. When you go on to physics next year, if you get to a test and you can't remember a formula, look at the units that they're giving you in the problem and line them up and end with the unit they're asking for. All right, so let's continue on. The mole ratio, real stoichiometry. There's going to be several different conversion factors that we're going to need. Remember, we always start with a balanced equation, and I want you to recall that 1 mole of any substance is equal to the molar mass, so we're going to need molar masses again. Just for grins, let's remind ourselves how we calculate molar mass. Noah, how do we calculate molar masses? Not Avogadro's. We add up the atomic masses that are in the compound. Okay. So first of all, write the balanced equation. Identify your known and your unknown, and then you're going to start with always your known. And then mole ratio, we're going to need that. We're going to need molar masses, and then sometimes we'll need volumes. This is a new conversion factor for you guys and gals. And that is at STP, 1 mole of any gas is 22.4 liters. Okay? What is STP? It stands for standard temperature and pressure. And standard pressure is 1 atmosphere. Standard temperature is 0 degrees Celsius. Okay? You don't need to know that right now because any gas problem you see in this unit, you can assume STP. We don't learn how to calculate at non-STP conditions until we get to the gas laws unit, which is after stoichiometry. Okay? So for now, if you see liters or volume, you can use the 22.4 liters per mole. You do have to memorize that. Okay? All right. So let's work a couple of problems. All right, let's start with this one. How many grams of copper 2 oxide are formed in the decomposition of 6.59 grams of copper 2 oxide? For some reason, on your notes it doesn't do this, but on this one, this really goes over here. So let's move this over here so we can look at it all at once. First step, do I need to balance the equation? No, yay for us. So I'm going to start with what they gave us, and I'm looking for copper 2 oxide. So 6.59 grams of copper 2 oxide. Now remember, I said the way you go from what you have to what you want is the mole ratio. Okay, but I'm in grams here. Can I go straight to the mole ratio? No, I have to be in moles of copper 2 hydroxide. How do I convert grams to moles? By the molar mass. So I'm going to add up the molar mass of copper 2 hydroxide. Copper, 63.55, plus 2 times 16 for oxygen, plus 2.02 for the hydrogens. So when I do that, I should get 97.57 grams per mole. So my grams cancel. So now I'm in moles. So now I can use my mole ratio. Everything is 1 to 1. So I'm going to say for every 1 mole of copper hydroxide, I can produce 1 mole of copper oxide. Now, because it's 1 to 1, you might be tempted to leave that step out. If you leave that step out on a worksheet or a test, I will take points off. You must show the mole ratio every single time. Okay? So I get rid of moles of copper hydroxide. Now I'm in moles of copper oxide. If it was wanting it in moles, I could stop here, but it wants it in grams. So how do I go from moles of copper 2 oxide to grams? The molar mass of it. Y'all are on point today. 63.55 plus 16 gives me 79.55 grams of copper 2 oxide. Multiply the top, divide by the bottom. However you want to put that in your calculator is your choice. If you're using one of my calculators, remember you can use that N over D key. Type in the top, type in the bottom, and hit enter, and that'll give you the answer. If you want to do it as a series, you can do that as well. So what do you get? $5.37? That is correct. We need 3 significant figures because of that right there. You will use what's given to you in the problem to get your sig figs. You will not use the mole ratio or the molar masses because those are exact numbers. Okay. Anybody lost, dazed, or confused at this point? Do we feel tentatively okay? All right, let's work another one then. No crying. Okay. First step is balance the equation. How do I balance this? What do I need? I need a 2 here and a 2 there. All right. I'm going to start with the 30 grams, and we're looking for grams of sodium sulfate. That's what we're going to try to go for. So we'll say 30.0 grams of sodium chloride. We need to do what next? Convert to moles using the molar mass. Good job. One mole. So I have converted to moles. Now that I'm in moles, I can use my mole ratio. So I look and I have 2 moles of sodium chloride. And I'm looking for sodium sulfate, and there's only 1 mole of that, so I'd put 1 mole of sodium sulfate. It did ask for grams, so I need to convert to grams. And how do I do that? Molar mass of sodium sulfate. So I would take 22.99 times 2 for sodium, plus 32.07 for the sulfur, plus 4 times 16 for the oxygen, and I should get 142.05. Cancel, cancel. So now I multiply by on the top and divide by the bottom, and what do you guys come up with when you do that in your calculator? So how many sig figs do we need? 3. So 36.5 is my answer. Any questions at this point? Okay. The next example uses volume, so I want to work that so you can see how to work volume. Okay. All right, so this one says how many liters of oxygen are used to produce 75 grams of SO3? So what is my first step? Balance. How do I balance this? Put a 2 here. No. Yeah. So now I should be balanced. Okay. I'm starting with the 75 grams of SO3. What is SO3 called? It is not sulfite. There's no charge on there. Sulfur trioxide. Thank you, Evan. Okay. I've got grams. I need to get to moles. So I'm going to use the molar mass. 80.07. Cancel, cancel. Now, since I'm in moles, now I can use my mole ratio. So there are 2 moles of SO3, and it requires 1 mole of oxygen to make that. Cancel, cancel. So if it was asking for grams, at this point I would plug in my molar mass of oxygen, but it's not asking for grams, it's asking for liters. And luckily they gave it to me right there. So for every 1 mole of oxygen, it's actually 22.4 for any gas. It's 22.4 liters of oxygen. So you use it like you would the molar mass. It's just asking for volume. So now multiply the top and divide by the bottom, and you get what? $10.5, because we needed 3 significant figures. All right. Yes, ma'am. Yes. I'm going to do this last example that starts with moles, and then I'll let you loose to work on your papers. Now, if you noticed in your notes, there's for the practice problems that are built into your notes, I gave you the answers so that you can work them out and see if you get the right answer. It's a way to check yourself. So I suggest if you've got a handle on this, you can go straight to the worksheet. But if you want to work some problems and see if you're doing the right setup, there's a way to check it. Okay, so let's do this last one, and then we are done for notes. This one wants to know how many grams is used when you have 85 moles of ammonia. Okay, so first we need to balance this equation. It's a little tricky. Anybody got it? Should be 4546. So we're going to start with our 85 moles of ammonia. Okay. Since I am starting with moles of ammonia, do I need a molar mass? No, I can go straight into my mole ratio. So for every 4 moles of ammonia, it's asking about oxygen up here, it requires 5 moles of oxygen. Okay, so now cancel, cancel. And so it wants mass of oxygen, or grams. So I'm going to have to do 1 mole of oxygen, and what is my molar mass of oxygen? It's not 16, it's O2, 32. Okay? So when I do that, what would be my answer in 2 significant figures? $3,400, which would be a lot of oxygen. Okay? Which 85 moles of ammonia is a lot, so you should expect a high number. So this is where you want to do a little bit of number sense and say, hey, 3,400 grams, that seems like a lot, but if I think about 85 moles of ammonia, that's a lot of moles. Okay? So worksheet is due on Monday, and if this video will be posted on Canvas later if you want to refresh your memory.